we are going to learn about phase diagrams. So we've looked at basically our kinetics lecture in lecture 4. So we've looked at kinetics. So we know the rate at which flux, or how material responds. So Fick's first law, C, we've got Fick's second law equals E grad squared C. So we know how material is going to respond in response to kind of some conjugate driving force. But now today we are going to get into a little bit, actually not a little bit, quite a bit of TD, thermodynamics. So we're going to learn thermodynamically what is the equilibrium state of a system. And we're going to see that materials can exist in many different phases. They could be solid, liquid, gas, vapor, plasma. They could be mixtures, basically these kind of solid mixtures. So there can be lots of different kind of phases that a material can exist in. So we need to figure out between solid, liquid, gas, basically alpha plus beta. So this could be like a BCC plus an FCC mixture phase. Which of these equilibrium states, which of these phases, which of these phases is going to be the equilibrium or lowest energy, or the equilibrium phase in a material? That's the question that we want to kind of answer and ask ourselves. What is going to be the lowest energy state? So given some combination of temperature, pressure, composition, so as a function of these variables, these extensive, or some of these are intensive and extensive variables, depending on these variables, what will be the lowest energy state? That's kind of the key idea here. And basically, it kind of all boils down to this. The thermodynamically stable phase is going to be the one with the lowest free energy at any given temperature, pressure, composition, etc. And the crossing points, basically where we transition from one phase to another, those are going to determine our phase transitions. So let's look at a very, hopefully straightforward transition. So I might have a little bar over here. Let's look at a melting transition. So at high temperatures, I'm going to be liquid. At low temperatures, I'm going to be solid. So let's look, before our melting temperature, what phase are we in? We are in the solid phase, lowest free energy, right? But as we increase our temperature, what happens? We get this crossover point where now the thermodynamically stable state at above our Tm, at T greater than our melting temperature, is going to be liquid. So you can kind of see that this is, if you see this bar over the top, it's going to be the molar. It's just normalized. So the molar gives free energy, and the molar free energy of a solid phase. So liquid, blue, solid, red. I'll try to be constant. So you can see this transition, and actually this is going to be a first order transition, melting. You'll see this quite a bit on your DSC lab, but anyways, this is a first order thermodynamic phase transition. But we can kind of do the exact same thing and draw out this phase diagram for the complete kind of spectrum. So when a solid melts, liquid boils, or what solids can sublimate directly to vapor. So you can kind of see on the next page right here how it would look again if we keep going up in temperature. So we see here, below here, we should be solid. Why? Lowest free energy. Between here and here, what are we? Liquid, and then finally vapor on this side. So it's just literally the key thing about this lecture, the one statement is this: lowest free energy wins. That's what this is all about. So the lowest free energy is going to win in this kind of framework. So that's how we're going to kind of figure out and see the different phases that a material can exist in. Now, I've kind of already kind of said this: alpha, beta, gamma. You see these in terms of phases. We know that materials can exist in multiple different crystalline forms or structures, depending on temperature, pressure, etc. What was the name of those guys? Allotropes or polymorphs. So iron, carbon, PbTiO3, lead titanate. So it's going to be useful to kind of see, okay, where are we? At what conditions will this be? Will it be in the cubic phase? So we know we're cubic when temperature is basically greater than 490 degrees C. We're tetragonal below when temperature is less than 490 degrees C. So it would be really, really useful, right, to have some type of diagram to show us the phase i.e. phase diagram. So we're going to get into the phase diagram and actually the Gibbs phase rule next time for a single component material. So look forward to a fun lecture of phase diagrams and invariant points and all kinds of other cool things. So we'll see you next time. Thanks. Bye.